Next up, we have an application that's more focused on electrical engineering. And this will be another application of a first order differential equation. And in this application, we're going to analyze RL series circuits, right? And so the R and the L, those letters are referring to the specific components that will be in our circuit. So let me just draw one of these circuits. Now, depending on, what sort of, are you using American symbols or European symbols? The symbols might be a little bit different. We're not going to get hung up on that. But basically, the R stands for a resistor. So we're going to draw our resistor like that. The L stands for an inductor, which is basically just a nice coil. And then any good circuit should have a switch, right? And then we're going to have a voltage source in this. So we're going to draw our voltage source like that, right? So I'll label this. This is really our resistor. This is our inductor. This is our switch, and this is our external voltage, right? So the shorthand for resistor obviously is R. For inductor, it's L, and then for the voltage, obviously V, right? And our goal is to, once we've identified or determined what our voltage is going to be, are we going to have just a constant voltage? Are we going to have a sinusoid or anything like that? Our goal is to figure out what is the current in the circuit at any given time. Once you flip that switch, right, you turn it on, based on the voltage, we should then be able to determine what the current is, right? So our resistance and our inductance is going to be constant, right? And then our voltage may or may not be constant. And if your voltage is not constant, then, the problem becomes a little bit more tedious. But if it's a constant voltage, the math tends to work out a lot more simpler. And before we go any further, let me just preface what we're about to do by saying there are many ways you can analyze circuits. We are simply focusing on the way that requires using differential equations. Not every time that you have to analyze a circuit, you have to turn to a differential equation, right? In fact, when you study, there are certain applications in linear algebra where you can analyze simple circuits where you don't have inductors, right? If you just have a voltage and you have a bunch of resistors, depending on whether they're in series and parallel, you only need basic algebra to analyze those. But when you add other components like inductors and also capacitors, which we will see in the future, and if you want to analyze it from a purely mathematical standpoint, and that's when you need differential equations, right? So we need to get a differential equation out of this. And we turn to Kirchhoff, right? So for a series circuit, containing only a resistor and an inductor, like the one shown there, right? Kirchhoff states the following. And the general principle, in fact, not just these types, but in many types of circuits, Kirchhoff says the voltage drop that that occurs across each component. So again, the resistor would be a component, the inductor would be a component. So Kirchhoff says the voltage drop that is experienced across each of these components, if you sum up those voltage drops, it has to be equal to your impressed voltage, right? That's basically what Kirchhoff says. Kirchhoff says the sum of the voltage drops, again, I'll pluralize it because you can have many, if you have many components, right? The voltage drops is equal to the, I'll say, impressed voltage. And it's actually another version of a conservation law, but it's more of an electrical version as opposed to, let's say, a mechanical version, right? In fact, we're going to use the mechanical version in the future. That one's going to be cool too. All right. So what I'm going to state now, and again, that's without any formal proof. I'm going to state the voltage drop that occurs across a resistor and across the inductor, right? And I'm also going to introduce the notation that we will use for the current. So if I of t represents the current at time t, right? So I'm again emphasizing that the object of our interest here is the current, and it is a function of time, and we're going to use little I to represent the current in this case. So then the voltage drop, in fact, let me do this. I'll make a little table. So I'll say over this component, we'll write down the voltage drop, right? And there are only two of them here, so I'll just make a little table, right? When across your resistor, so across the resistor, the voltage drop, and again, this is something that we saw just as algebraic applications. It's simply your R times I, right? So your resistance times the current, right? Across the inductor, something a little bit more interesting happens, right? And this is where we actually end up with the derivative. It's your inductance times the rate of change of current. So di dt, right? Oh, forgot to write the word drop there, right? So we're going to use this law coupled with what we know about these voltage drops, and then we can write down what the differential equation is for an RL series circuit. So again, I'm going to take the voltage drop across the inductor, so that's di dt times L, plus your R times I, that's the voltage drop across the resistor, and Kirchhoff says that these two things must add up to our external voltage, or the impressed voltage. Most books use V of t for voltage. I've seen some that would utilize E of t for electromotive force. They might do that, obviously, because of the relationship between voltage and electrons and so forth, right? So, but nonetheless, this is the equation for an RL series circuit, right? And again, our goal is to find the current as a function of time. So we know what the current is at every possible instant. So let's take a look at an example of this, right? And so instead of drawing it, I'll just kind of state what we have. So we have an RL series circuit has a voltage, misspelling voltage there, has a voltage of 5 volts, right? A resistance of 50 ohms, so it's a lot of resistance there, and an inductance of 1 Henry. Henry is the unit for inductance, named after a person. In fact, these are all named after people, right? And no initial current. So, and no initial current. Express, here are our instructions. Express the current as a function of time. So express the current as a function of time explicitly, right? Okay, my thing, there we go. Let's write that. So explicitly. All right, there we go. Now, the nice thing about this, again, so for us, L and R will always be constant. So if you look closely at this differential equation, what do we see? We see that it's linear, right? In fact, RL circuits is an example, much like Newton's law of cooling, of a linear model. It could be more, it could be separable and so forth, but for sure it's going to be linear. So again, we're going to be using our integrating factor method. So let's set up the differential equation. So our L is 1, so we have di dt. Our resistance is 50 ohms, so that's 50I. And then our voltage, we have a constant voltage source of 5 volts, right? So that's our differential equation. Pretty straightforward. And it says, and no initial current. So that means I of 0 is equal to 0, right? And the units for current would be amperes. So I'll write that here, right? And again, what we want to find now is the current as a function of time. All right. Well, it like I said, it's linear. This technically is also separable. To separate it, we would have to move the 50I over here and then divide by that entire quantity. So again, not going to do that. It's set up perfectly for the integrating factor method. Here is our P. So this is our P of t. This is our Q of t. So our integrating factor, it's e to the integral of 50 dt. So we have e to the 50t, multiplying through by e to the 50. So we end up with e to the 50t di dt plus 50 e to the 50t times I. And then on this side, we have 50e to the 50t, right? So that's pretty good. And then when we look at the left-hand side, we see the pattern for our reversing the product rule, right? Because if this is my f, then this is f prime. And if this is g, then this is g prime, right? So the left-hand side is the derivative with respect to t of e to the 50t times, again, our unknown, in this case, current. So we end up getting, well, this expression on the right-hand side stays the same. Now, integrating both sides, we will have e to the 50t times I, in antiderivative of 5e to the 50t dt. E to the 50t times I is equal to, and we divide, so when we integrate, we'll have 5 over 50 e to the 50t plus c. So we end up getting 1/10 there. So we have e to the 50t times I is equal to 1/10 e to the 50t plus c. So when we, let's see here, divide through by the exponential function, we'll have I, and that's equal to 1/10 e to the, this exponential goes away, so we just have the constant 1 over 10, and then plus c e to the negative 50t. So this is our general current function, but we know that when t is equal to 0, little I is equal to 0, because again, the condition said that there was no current initially, right? So when t is equal to 0, I is equal to 0. So we have 0, we have 1/10, and then we have plus c times e to the 0. So c would have to be negative 1/10. So here is our current as a function of time. So it's 1/10 minus 1/10 e to the negative 50 over t, and then this would be amperes, right? And this would be that function. Now you look at this, with such a huge negative coefficient in the exponent of the e, this term, the e to the negative 50t, that approaches 0 very, very quickly, right? So, you know, this component of the current, it decays very rapidly towards 0, and then we're left with this constant term. Now, again, we're not going to go deep into the electrical engineering, but I am now going to introduce a couple terms and a way of kind of classifying each term in your current based on what happens to that term as t gets very, very large, right? So in many applications, right, involving these circuits, so in many applications involving circuits, not just of this type, but other types, so series circuits, well, actually not just series, let me just say circuits, so involving circuits, we would like to know what happens to the current as over a long period of time. So we would like to know what happens to I of t as t goes to positive infinity. So this is basically saying, if you left that switch on in your circuit for a long period of time, what would your voltage end up, what would your current end up being, right? So we'll talk about several responses now. So the current, right, in other words, the output that we get from this is often referred to as the response to this system, right? So I of t is often referred to as the response of the system. And by system, I mean the circuit. In other words, we set up the circuit, right? We set up the circuit, we have our voltage, we have our, so think about it this way. We have our voltage, we have our resistance, we have our inductance, and all of these things go into the circuit, right? And it builds a circuit. And then what do? We turn it on. So we turn it on, and then what we're then going to analyze is the current, right? So you can think of these as the inputs, right? And then this is the response, right? It's like the stimuli and the response. This is just an electrical analogy of that, right? So we refer to I of t of the response. So depending on, it usually depends, if you keep your resistance and your inductance constant, right? The response is going to rely heavily, or depend heavily, I should say, on the voltage, right? So how do we describe the different responses that can occur as t goes to positive infinity, right? Well, let's take a look at this example that we have. So in this example, here was our response. It was this function. So e to the negative 50t. Well, so this response has two terms. It has a constant term, and then it has this exponential term. So as t goes to infinity, this term, so I'll say, the limit as t goes to infinity of 1/10. Well, because this is a constant, it never changes, right? So it's 1/10, right? And then what about the other term? So as t goes to infinity, well, the limit as t goes to infinity of e to the negative 50t, well, let me rewrite this exponential function. So I can write this as 1 over e to the 50t, which means I now have essentially a fraction where the numerator is constant, but the denominator, right, is going to positive infinity, right? So we have to think back to our limits at infinity properties from Calc 1. In this case, we have this form. It's not an indeterminate form, but it's a form where the numerator here is a constant, right? And the denominator is getting arbitrarily large. So the entire fraction approaches 0, right? Whenever you have a term in your response that approaches 0, we say that term is transient. So we describe this term, so the term e to the negative 50, because it approaches 0 over a long period of time, we say the e to the negative 50t is a transient term. In the sense that it dies away, it approaches 0, so it becomes negligible over time, right? So this term, even though it's present, it does not have a significant impact on the overall response in the circuit. Whereas this 1 over 10, right? It never goes away. It's a constant. So whenever you have, so putting this all together, right? So therefore, the limit as t approaches infinity of I of t. So if I now look at my entire response all together, I know that it is going to approach, well, that should be minus, because I have a minus there just to be consistent. So it approaches 1/10 amps. And whenever your current approaches a non-zero constant, then we refer to that constant as the steady state current, right? So we say, so because of this now, we say this response has a steady state response 10 amps, right? So you have some terms of your current that, even though they're present, they become negligible for larger values of t, and you have some terms that will never go away. You have some terms that, again, depending on the components of your system, right? Your V and your R and L in this case, where you might have. So here are some other responses, and what I will do is I'll show these graphically, right? Since we don't have particular any other terms to illustrate it here, let me just show you some graphs. And each of these will represent what happens to your current over time. So for instance, let's say it was just all the terms of your current would be transient. Then your current, it would start out somewhere here, for instance, and it could possibly just decay like this, right? So it could look like that. Current could also be negative, but I'm not going to draw it a negative version of this. But here's another way that your current can be transient. It doesn't have to have this strict exponential decay. It could oscillate like this. It could do something like this. Right? And both of these, as far as plotting the current versus time, these represent responses that are transient, right? So both of these are transient. But they decay in different ways. This one, there is a it oscillates, but what happens is the amplitude decays over time. All right. As far as the steady state, like this one, if we were to plot our function, what you would see if you were to plot your I of t with respect to t, you would see something like this, right? Where it would be approaching a constant, but a non-zero constant. So whatever this, I'll just call it like I sub 0, right? Which is not equal to 0. And this would be the steady state value, right? So, or the response here now would be steady state. So this would be an example, right? There are other ways the graph could look. I'm just drawing just examples to illustrate each of them. Now, depending on your voltage, if you have a sine wave, if you have a sinusoid as your voltage, then you would likely end up with, or you could end up with something that's sinusoidal like this. So let me just give you one example. So you could have a response that does something like this. Like, so early on, it seems exponential, and then it could start to level off and look like this, and so forth. And over here now, it becomes periodic. So in the long term, not down here, right, but long for larger values of t, again, if you left that switch on for a very, very long period of time, your response would be, and in this case, we would describe it as being periodic. Right? Just like, like if you just look at this part of it, it looks like a basic, sine or cosine function, hence periodic. And then you have those instances where you question your design of your circuit because it goes up in a puff of smoke, right? It just, things break. And that's when your current becomes unbounded, right? So that the current it increases, let's say exponentially, it increases exponentially. That's never a good thing, right, in your design. So I'll just say that here your response is unbounded, right? Again, there are other ways it could become unbounded. And I think I'll draw one more thing just to illustrate this. And this, what I'm about to draw, leads to another concept which we don't go deeper into in this course, but where you might have your response look like this. So it oscillates, but if you notice, the period just keeps getting bigger and bigger, right? So it's still unbounded, but not in the way where it's exponential, right? So lots of really interesting things can happen from these simple circuits, and there's a lot of electrical engineering theory that can go to help you kind of predict the different types of responses you can observe. We will be able to determine the responses simply by looking at the solution to our differential equation. We can identify that, for instance, in this example, we had a constant term and we had a decaying exponential term. So we knew, again, when you added those two terms together, what would happen. This term approaches 0, this term approaches 1/10, so their difference approaches 1/10, and then that's where we get the steady state response, right? So there you go. A look at electrical circuits, and some of you might be experts, some of you may know more about circuits than I do, and more power to you. But I like using differential equations to analyze certain physical systems such as circuits. So if you like it too, let's just hop on over to the next video and continue the fun fest. See you then.